In this video, we pick up at Maxwell's equations and go on to discuss some of the major experiments that evolved our understanding of the nature of light and matter. We'll cover the Thomson and Rutherford experiments that revealed the subatomic structure of atoms and discuss de Broglie's stunning proof that matter, like light, also exhibits wave-like properties. Combined with Einstein's explanation of the photoelectric effect, we arrive at the greatest paradigm shift of modern physics, the wave-particle duality of light and matter. We'll wrap up with a derivation of a fundamental principle of quantum mechanics, the Heisenberg uncertainty principle, and how it sets a hard limit on what we are permitted to know about reality at the smallest scales. Speaking of starting point.
Yeah, so welcome back. Last time I was over, I introduced you and teased you with the idea of understanding, well, first off, what a quantum jump was and how scientists have recently been able to catch and reverse these things mid-flight, a quantum particle shifting from one state to another and them saying, no, go back. It's a really cool thing. And then, of course, to understand the context of why it's such a cool thing that scientists are able to do that, well, we had to just really quickly go over the entire history of human science and physics in general with our understanding of light and matter. It's fine, right?
No big deal.
Easy stuff. We did all of this stuff where we first talked about light potentially being a particle and how that theory worked really well for some things, but as is good with any science, scientists just can leave well enough alone and went, hey, there's a spot there that we can't explain with this, and then realized, well, we need a wave. We need wave theories, and the phenomena we expect from waves popped out quite nicely. And then, in fact, what type of wave it was falls out very nicely from Maxwell's equations, right? You can derive the wave equation. And it gave a very solid set of evidence that, yes, light is a wave and something. It's an E and a B. It turns out, actually, that I believe it was Faraday initially proposed that, hey, with this popping out, maybe light doesn't need its own medium. It doesn't need a special medium. It is its own medium. Now, that wasn't really picked up. He didn't follow through on the math on that and the implications, so it's Einstein that later discovered that. But being a good scientist, later on, just a little while later, Einstein and Planck realized, wait, guys, I know waves are strong, but we need particles again. Leaving scientists in the unenviable position of going, okay. Okay, I don't know. Waves or particles.
And this is a testament to science's power, that it ever evolves as theories and methods get better.
Absolutely. So what's funny is that our understanding, and I think this speaks to the dichotomy that is difficult for scientists to maintain, is that you can have these theories that you have such confidence in because they really do explain well what you see, what you experience, the phenomena that you're paying attention to, and go, oh, okay, I understand this thing. But any good scientist knows not to leave well enough alone and to look for other phenomena and see, well, does my current theory still explain this? I have a friend, and I get into arguments with him all the time about how scientists can know anything. Right? When we're doing physics, is it really possible to have a full understanding and actually know things? And to be fair, he is correct. Science can't prove anything. What it does is give us models that we can make better approximations of reality around us. So you have to kind of hold this dual position of having faith enough in your model to push it, to see what it can do, what it can explain, but also having a skepticism of knowing that no matter how good this thing is at the moment, I might be able to find things where I might be able to find regions of energy, or I might be able to push my theory into a realm where it no longer is able to explain things. And then all of a sudden I'm left asking myself, how do I reconcile the current theory that I have worked so hard on with this new phenomenon that it can't explain? And even worse is when you end up with something like this with light, where we are where at the current time it's in at this point in the history of science, you're stuck saying, well, I need one thing. I need waves, and I need particles to explain this other thing. I need light to both be a wave and a particle, depending on the situation. And you're stuck there going, I can't reconcile these two things at the same time. How do we deal with the need for both of these at once? Now, if you remember at the beginning of last time when I was talking about light and how, we kind of had a notion of what matter was, right? It's stuff that I can hold on to. It's probably made of particles because I can physically hold on to it. It's not this wave-like matter. And, just like any good scientists, eventually we couldn't leave well enough alone. I had to question that. So let's take a step back and go through, since it's important, like I said before, to understand the context of things. Let's take a step back and go through our theories about what matter was, right? Now, we had different theories about what actually made up stuff, what made up physical matter. Around the 19th century, people kind of had just a general confidence that, not even confidence, a knowledge that the matter you had followed Newton's equations, and you couldn't really probe it any further than what was available with the technology that they had available.
So the microscopic was just not available at the
right,
time.
because there, even since the days of the Greeks, right, there was a question of, like, I could take this table and I can cut it in half, right? And then I can cut one of those pieces in half, and I can keep doing that. And the crux of the question is there a point where I can't anymore? Is matter something that's continuous, kind of like, grape jelly, basically, where I can just imagine just infinitely dividing that into as many pieces as I ever could want? Or is there a limit? Is there a hard stop to where I can keep dividing, right? And that was a big debate that was throughout, like, even with Greek philosophers, right? You had the people who were like, no, matter is continuous. And then you had Greeks who were the atomists, atomos, meaning indivisible. The idea that, no, there is some smallest piece that you cannot get any smaller than. It was Dalton's work in the early 1800s. Dalton was a scientist working on chemistry. He was trying to understand how two elements, or two different, clearly different things of stuff, if you interact them, will give you new stuff, different stuff. And what he realized is that whenever you, by finding different interactions, he was able to realize that, there are these elements these are the pure substances, right? Elements that we now know as hydrogen, helium, oxygen, things that are the same no matter how you probe them or subdivide them out. And then there are mixed substances that you can tell through reactions that allow you to split up the compounds. Tell, this thing, like this table, is not just one element. It's a combination of 13 carbon molecules mixed with 36 oxygens and 36 hydrogens and 10 oxygens, or something like that.
Mm-hmm.
Right? This being wood is going to be made from a organic compound, and those are the three basic elements that make up organic compounds. And what he noticed is that whenever I have a substance and I try and I do the analysis to try and figure out what it breaks up into elements, that these things always show up in the same proportions, right? It will always be that like, no matter where I pick out on this table, when I look at the fundamental decomposition of it, it will always show up carbon, this many carbon to this many hydrogen to this many oxygen.
Right.
Right.
So there's an established ratio,
right,
that composes the matter of this table.
And with that ratio always showing up the same for each substance that you try and do this on, the natural conclusion is, there are these fundamental pieces that combine together that give us everything that we see, right? The difference between the glass here and the table is about how those ratios, eventually it was discovered, is about how not only the ratios, but how they can physically conform themselves into different shapes. That's one of the hardest part of organic chemistry, understanding how those molecules will interact, is the fact that they can take numerous configurations. It took a while to figure that out, but first what we had to do, and eventually discovered, is that the atom wasn't the smallest piece of matter available. Even though that's what we called them atoms in reference to the idea of it being an indivisible particle, it turned out there's actually a way to subdivide that even further. You can get subatomic particles. This is done by Thomson and Rutherford, who eventually figure out how the structure of the atom is broken down into its subatomic particles. Now, the way that we figured this out was, first we discovered the electron, because in the 1800s we discovered how to manipulate and produce electric current at will. Right? We were able to use chemical reactions to figure out, oh, okay, I have a battery, and that can give me voltage, and that can give me current. So once we get to the mid 1800s, we start to develop the tools necessary to start probing. So all of a sudden, once your technology has caught up to the point where you have a new tool to probe matter, it's important to test it out, because that opens up new opportunities to see what will this thing, right? What does this table look like in the lens of electric current versus in the lens of light bouncing off of it to us? Once you develop new technologies, it's important to use those technologies to check whether your assumptions are the same in that, new view, if you will, compared to what you already believe, right? Mm-hmm. And yeah, the first thing that popped up.
Oh, it's so cute.
I have this. Oh, let's see. Where have I put everything else? Oh, well, it's very small.
There we go.
Zoom in a little bit here. Yeah, so you'll actually recognize this device here, this setup. This is similar to, or exactly what is called the photoelectric effect. So what you have is you have a battery on top providing voltage, and you have wires connecting from that battery into a glass tube that's either evacuated or filled with limited amount of gas. And you charge the two plates with that battery, right? The battery has a positive and negative end, so the plates will be positive and negative. And what's interesting is that if I have a battery with a high enough voltage, it will send out lines that with the gas you'll be able to see. And what that turns out is it's electrons moving through the gas from one plate to the next, because the voltage is high enough to give the electron enough kinetic energy to move through the gas. And as it goes through the gas, it's kicking off, it's interacting with the gas molecules and causing those things to bump up in energy and then irradiate out. So that's how you're able to physically see electrons moving through gaseous material. This is it's actually fun. You could do an experiment that is frequently done in undergraduate physics lab called the where you use a Helmholtz coil, basically a set of two things that gives you a consistent B field that if I shoot, electrons through, because they're charged particles, and a B field, right, a charged particle moving in one line will get curled. And so you can actually have the electron move in a full circle. And you can relate the radius of that circle to the ratio of the charge and mass of that particle. Really cool thing. And you're able to physically see it because the electron charges up, like interacts with the gas and causes it to, some of the atoms in its path to get excited. And then when those atoms go back down to the ground state, they do that by emitting light. Right?
And that's one of the ways we experimentally confirm those two constants you had in Maxwell's equations, right?
Right. Once you have the ratio, what you need to do is you need to determine one or the other. And so once discovered, so the only way you can have, this is with this experiment. Thomson realized, oh, I must have these individual particles. So particles are what's carrying charge. But the only thing that makes this up is neutral wire. So the source of these particles must be the neutral material. So it must be, since it's neutral, there must be some negative charge particles, but there also is some positive charge in that. And that way I can balance out the positive and the negative to end up equaling zero.
When there's no voltage source applied.
Right. Because when I material I touch, I'm not getting shocked. I have no electric charge.
Unless you're my
overall.
Wife. She gets shocked on everything.
Oh, goodness. Hey, man, Midwest winters are the worst. Let me tell you, I walk around the office, before COVID times, and I would just, every winter, just shock. Every door handle, it's the worst. To the point where now I'll just I'll punch door handles first and then open them.
I used to go down to Vegas with friends of mine.
Yeah.
And Vegas was so bad one year that I would just carry around a coin and they have metal rolls or metal poles, handholds everywhere, all throughout the hotels and everything. And I'd just be touching like every 5 seconds because it would get so bad.
Yep. I'd do the same thing. Punch door handles first, just in case, and touch the cabinets that were metal to help decharge every time I walked past.
Yep.
So the way that Thomson was able to understand that these were negatively charged particles is the little discs here, is that he would set up another electric field perpendicular so that the top plate was charged positively. And he saw that, these things curl up towards the positive charged plate, which means, from what I know about electrodynamics, is that positive things and negative things attract. So if a negative thing is being attracted towards a positive plate, it must be that these particles that are streaming through the air are negatively charged. And so that was the first peering into the notion of the structure of matter, like the structure of the atom itself, because we knew that matter had to be constructed of neutral particles because of how it interacted with electric fields, right? I put an electric field on this table, and it really doesn't do anything. It doesn't move, which my theory tells me, it must have no charge to it. But clearly, I had plates that had, if I just leave them alone, right, just put it in the thing, it doesn't. If I put a metal plate in the middle of this, it's not going to move anything. Instead, what's going to happen? It doesn't move either way. So
not until you apply the battery.
But once I apply the battery enough to two sources and basically evacuate enough gas so that there's nothing that really there's less energy required to stop the electrons, then you can see this phenomena. Now, granted, you can have the movement of electrons between two highly charged plates. This is a very basic model of what happens with lightning strikes. It just happens that air takes enough energy to ionize, to let the electrons pass through them, that you have to crank up the voltage to excessively dangerous levels, because you need all the energy of a lightning strike in order to get that movement of charge. You can the very basic model is to say, the earth and a cloud are two ends of a capacitor, and once enough voltage is built up, bam. But it's kind of hard to get that much voltage in a battery, so you got to evacuate the chamber, which is why you have this setup here. Right? You got to make sure that the electrons have a much easier time getting through whatever gas you have. Right. But that first piece then led to interesting theories about what must the structure of atoms be, right? We knew that you had small negative particles. So the question then became, what is the structure of the positive charge in the rest of the atom? Thomson proposed what he called the plum model, which was the idea that you could think of the atom as a plum, where the seeds in the plum, the small, hard, discrete bits, were negatively charged. And then there was a mushy, positive, fruity flesh bit that stayed structured, but it was hard to pull out because, you couldn't interact with all of it at once. So that's why the charge carriers you see are negative, because it was so dense, because the negative charges being so densely concentrated, it was easier for the electric field to pull those pieces out versus moving the fleshy piece altogether.
Okay.
Right. That's effectively what he was trying to, propose. And that was the accepted theory for quite a while, until another scientist couldn't leave well enough alone and went, let's check. And that's where a gentleman by the name of Rutherford comes in. And he has a famous experiment where effectively we had also discovered radioactive material. So material that kicks off here, what he uses was stuff that would kick off alpha radiation. So effectively there are some materials.
But they didn't realize that at the time.
Yeah, they didn't. So he knew that what it was kicking off was a charged particle, a positively charged particle, but quite classifying what type of radiation it was, wasn't fully done. But here, what we know is that the material he was using, I believe, was it rubidium? I don't remember off the top of my head, and I should have looked that up, but oh well. What he was measuring would kick off alpha radiation, which is effectively the core of a helium atom. It's 2 protons and 2 neutrons. He didn't know that. All he knew is that when the particles that this thing emitted was positively charged because of how they behaved in the field, and it shot off and fast. And clearly, since it's a small, it's coming from it's atomic radiation, it's small. So I should be able to probe some material with this and see, based on how these charged particles behave moving through some material, I should be able to get an idea of where the charge shows up, right? How the charge is concentrated in that material. So what he did is he got a couple of his grad students, because grad students are always useful for labor like this, and he told them, okay, pound out some gold foil and make it really thin, because gold foiling has been a technique that's been around forever. It's a nice malleable material, and he wanted something that you could get as thin as possible so that this alpha radiation had the best chance of going through it, right?
Assuming you could go through it.
Right.
Well,
these things he knew were pretty. If you made it thin enough, right? No matter what it is, as long as I make it thin enough, anything can go through it, right? Give it enough kinetic energy.
Right.
And so you wanted it thin enough that the alpha particles would be able to go all the way through. And so what he set up, and the idea of the plum model, is that, you have your source, let's do this. You have your source of alpha particles, and you have gold foil. Let's say here it's you don't know what it is, but it's some very thin sheet. You assume that the alpha particles will be able to fire from here and get all the way through it, right? Now, the idea being that positive charges will repel each other is that if the plum model is true, as these alpha particles go through here, based on whether there's more material here or here, right, the particle should not just move, should deflect as it goes through the material. If there's more positive charge here, then the force that it exerts on the alpha particle going through it will be greater than the force that this section of material exerts on that particle, and so overall you would have an upward trend. If the particle goes through a place where, oh wait, no, here is more material than down here, then I would have a downward trajectory. Right? That's what the plum model told us to expect. Right? Now, when he actually did the, and so in order to verify this, basically what he did is he set up a detector that ran this detector here. So this would basically be like photodiode paper, where if a charged particle hit it, it would light up. and it would stay bright in that spot. Okay, so you're able to tell, okay, as a alpha particle goes through the gold material, where does it end up on this, on this material? And you can measure that angle. So the expected result is, oh, okay, I should get, alpha particles. They're a little deflected up, either up or down. What he found is that most of them actually did nothing. Most of the alpha particles that they shot went straight through, had no deflection either way. But about 1 in 8,000, I believe it is, you would have some severe backscattering. The gold foil would, the alpha particle would hit the gold foil and then come back at you. Which, if you're expecting, tissue paper, basically the dynamics of tissue paper and a bullet, right? That's not exactly what you expect. In fact, that's the exact analogy that Rutherford described when he was reporting these results. It's as if I fired a bullet at tissue paper and it comes bouncing back at me. And the only way you could reconcile those two facts is that, okay, it must be that this alpha particle is, when it backscatters, is hitting something very dense and tight, that even though I've imparted so much momentum, this weighty thing says, no, I'm not moving, you move, and that you get reflected, right? Just like if I take a tennis ball and throw it against the side of a building, the building, because it just has so much more mass, says, nah, I don't care about Newton's third law. I'm going to wiggle a little bit, but you get all this momentum change. So the ball hits the wall and then comes flying back at your face, right? Mm-hmm. Same thing here. That's according to classical mechanics, that's how we know the interaction between small things and big things. Small things with lots of momentum and big things that are just sitting there will happen. You get these giant reflections of velocity because, you know what? If you've got that much discrepancy between mass, that's how it happens. And so from this, you get the classic picture of what we see, with the Bohr model. The idea that, okay, it must be that the structure of the atom is some densely region plus charge, and then on the outside of that, you have the negative charges.
How do we come to that conclusion based on the bouncing off the gold foil?
So you have to have dense positive regions in order to have your alpha particle bounce back at you. But remember, the thing you have to also reconcile is that the vast majority of your alpha particles have no deviation at all. So the conclusion is okay, the overall space of an atom must actually be empty space, right? Because you're not interacting with
neutrally
anything.
Charged.
Right.
Okay.
Because if you had the positive and negative together on the same spot, you would have no deflection at all, right? If I had something that, as I peered it, no matter how closely I looked at it, it was neutrally charged, then I should have absolutely no deflection. The fact that I do have some...
So what would happen instead if it was both? When you say deflection, are you saying that not only is it bouncing back, but it's bouncing back as if it were repelled by something positive?
Yeah.
So it's coming back with even more velocity than you would expect if it was just a bounce.
No. You not repelled. Like, the repelling is what causes the bounce back to begin with, because but you're not going to get when you have if I have if I have a solid ball and I throw a ball on it, the velocity that it comes back at me is the same velocity that it went into it with, right, minus friction or whatever. And that's effectively what this will give you as well. Even electric potentials, they don't kick back with more velocity than what you get as you get closer to the potential, to the source of the potential. But you do get, that wall bouncing effect. But if it were true that the structure of the atom where that, the negative and the positive were on top of each other. And so you had truly neutral, phenomena all the way through, and that electric current somehow was just able to pull out the negative. Then if, gold, it's a neutral material, so neutral atoms should never have any deflection of the positive charge. So what we know is that, negative particles come out in discrete capsules, and there's no reason to assume that they change in their dynamic from, being a small particle when they're outside of the atom, when they're outside of material, to being something, more loosely combined with the positive charge on the inside, which is why you have the Plum model. Right? Said, electrons, the electric charge, are in discrete packages, in discrete particles. And then the idea was, to compensate for that, we just have a mushy positive charge all the way throughout the atom to make it neutral everywhere.
Okay, so I think where you're losing me on the explanation here is that why is it, because we know the tennis ball, when you throw it at the wall, the tennis ball is basically neutral, and the wall is basically neutral, yet it bounces off. Okay, so why is it, if I were to take just a proton and throw it at the wall, it would bounce off as well, right? It would just all of a sudden get stuck in that wall. Okay, so clearly it can bounce off whether it's different or if it's the same charge.
True.
So why is it if I take the proton here that's coming from the radiation, the alpha particles, and if it wasn't positive, what they're bouncing off, what would they do differently?
So
if it was truly just a neutral blob, would they bounce? Would they stop and just fall to the ground?
Because what I have set up here is that it's not, initially when Rutherford set up this experiment, right, he didn't expect it to be a wall and a tennis ball. It's a tissue paper and a tennis ball, right? The idea was, this thing, I've made my material so thin, so massless that, the ball that I'm throwing should just be able to parse right through it, right? And if the average density of the gold was, the same if the density of the gold all throughout matched the average density, basically, if, the mass of the atom was spread out throughout the entire size of the atom, then you would expect to see some slowdown of the particle.
Okay.
But it still should be able to make it through. Right, it would be able to. The idea being, if it has enough kinetic energy to get through whatever energy it needs to deposit to break the bonding, of that gold molecule, of that gold atom to the rest of the gold atoms around it, right? But the fact is that it doesn't have that deflection from hitting that material. Instead, most of the time, it's as if it passes through empty space. It's got no deflection at all. And when it does hit something, instead of a small deflection, instead of losing energy, but just, a small angular deflection, instead it's as if it did hit the wall.
It's presenting as something much heavier than the alpha particle.
It's presenting as something much heavier than the alpha particle, and much heavier than would be expected of the average, density for the alpha particle hitting that region, right? If you took the average mass of a gold molecule and then spread it out throughout the entire space that it would occupy, right, you would expect, granted they didn't have this knowledge at the time, this is part of why you're probing it, right? They wouldn't expect that dynamic, that interaction. You would expect it, you have this alpha particle coming in here and it hits this region of the gold molecule, so this region, we know the density of that region would interact with, more of the mass should be able to punch through. And instead, when it actually hits a region of positive charge, it bounces straight back.
Okay.
Right. Now,
it's that when it hits that region of positive charge, it bounces straight back. I think that we're getting a little caught up in this. If we just take this analogy and we just scale it to macroscopic, like obviously if I take a bit of gold, let's say I take a cube of gold like this big, and I flatten it so that it's as thin as tissue paper, I should be able to just poke my finger through it. Now, what he was doing is he was expecting that to occur no matter where he hit that that gold foil.
Right, because
But if I had hit the cube with my finger, obviously it wouldn't bounce through, and I would just be repelled back.
Right.
Because the mass is no longer distributed smoothly across a large area. It exists as just a small chunk.
Right.
Okay.
Yes.
Right. Which means that the implication of this, which it's not clear to me how whether it being positive or neutral or negative matters here. It's just the fact that distribution of matter is such that it's clearly not a smooth, continuous region. It's actually clumped up into little tiny areas.
So it's thin enough that the main dynamic between the particle you're shooting at it and the gold foil should be entirely the dominating factor should be electrodynamic. So if you're shooting through something that's neutral, you're shooting a positively charged particle through a region that is not charged, then nothing happens, right? The particle doesn't deflect in any direction. If you hit it, if you have a particle heading straight toward a positively charged particle heading straight towards another positively charged particle, eventually the pushback that those two positively charged things,
right? That's what I was alluding to originally.
Will push it back, but if the density of that positively charged region that you're shooting towards isn't big enough, right? It will happen that the electron your shooting particle will pass by it and have either just a little deflection, or it will have a little bit less kinetic energy. But instead what's happening is it's coming in and then bouncing back as if there's a lot of charge, a high density of positive charge forcing it back, right? If there's only a little bit of positive charge, right? If there's a low positive density, whoosh.
This is so hard to try and do because we're not using the words Pauli exclusion principle or anything else like that
Yes.
actually explains why we
Yes.
see real rebounding in matter. So, okay.
Yeah. It's like, and it was long thought, right, with this kind of discovery of subatomic particles is that, okay, the reason why you and I don't go through this table is because on the tiniest possible scale, right, the thing that interacts with each other first are the electrons from this table and the electrons from my hand. So, eventually there's a positive charge. There's
Right.
a repelling and like, I don't sink in. But it turns out if you actually try to calculate that, right, you try to calculate the electrodynamic potential, but knowing the size of an electron and everything, you realize, oh no, that's not enough force to stop me from going through this table. There's extra things that quantum mechanics will eventually say, oh yeah, there are these principles that like, okay, these electrons are really unhappy with occupying the same energy states. So when you try and put it in there and you're trying to meld with the table, the two electrons go, no, please don't. And they do that harder than any electrodynamics ever could, right? But yeah, so the idea is that if you had you can, from experiments with gold, you can tell how many electrons should be there in an average, like on average in a gold molecule, right? And since it's neutral, okay, this is how much positive charge must be in there. And if I spread that throughout the entire volume, I don't expect that much resistance, right? It'll deflect a little bit.
Right.
But the fact that it hits and then sometimes bounces back means that there must be these regions of very highly dense positively charged regions, right? These very dense things that, as far as the electrodynamics is concerned, look like a solid wall that you're hitting and bouncing back on, right?
It's interesting they come to these conclusions because they didn't have the tool that I have,
Yeah.
which is knowing about Pauli.
Right?
Yeah.
But so reconciling the fact that occasionally you hit something and get these massive deflection and that you never have anything going through at all. Oh my goodness. Like that's how you reconcile. It must be that all the positive charge are in these tightly, densely bound regions. And then since you have to have a negative particle somewhere, it must be that the negative is on the outside, right? And that's how we get basically to the precursor of the Bohr model.
Okay.
Right. Yeah.
Now that I've sidetracked you.
Enough. Oh, man.
Proceed.
At this point. So now, okay, we have a good understanding of atomic matter, right? Oh, atoms are these things. They're split up into positive particles, and there's positive subatomic particles and negative subatomic particles. Hooray. We've got an understanding of how matter is. Boy, isn't that great. And boy, did it not take long for someone to decide not to leave well enough alone and ask, we've got this phenomena over with light, right? Because as Rutherford is doing these experiments, this is around the same time that, the Planck discoveries are happening as well. It's like, oh, wait a minute. We thought light was a wave, but now it turns out to be particles that we need to explain. And a gentleman by the name of Broglie thought...
What specific thing was it that led us coming back to particles?
You had, for light, you had Planck's idea of how to solve the ultraviolet catastrophe of black body radiation, right? That was the last thing that we talked about last podcast. And we talked about Merman's challenge, where effectively, in order to avoid predicting infinitely energetic low wavelength photons, you could discretize the wavelengths that were possible for photons to take on, and you discretized the way that the energy that they could interact with matter by. And that was also able to explain the fact in the photoelectric effect that when I have this charged up, I don't necessarily need a battery that's cranked up enough to cause photons to stream across this gas chamber. I can set up, if I evacuate the chamber with enough of gas and try and make it as vacuous as possible, I'll still have some resistance to electrons moving across, even though I've set up a potential. But what I can do is I can shine light on one of those plates, and that'll cause particles to stream from one side to the other. So somehow, light is giving energy to these plates, to the electrons in the plates, giving them enough energy to kick off and be excited to fly across the gas chamber to complete its transition.
Okay, so if I'm understanding correctly, we have two concepts here. One is that we have to discretize the energy that light has. Mm-hmm. We can't infinitely cut down that energy that it has and keep cutting it in half. So there's a quanta, there's a packet that is right. The minimum amount of energy that light can have. Right. And then the other thing is that light seems to have kinetic effects.
Right. Well, we already knew, like, that light has kinetic effects because we know that light has energetic effects because if I sit out in the sunny day, I feel hotter. Right. Right. I'm getting energy from somewhere in order to raise my, the temperature of my skin. The thing that's strange about the photoelectric effect, because, okay, we already knew that that light has energy, so I shine it on the plate and, it's enough energy to kick off these electrons. But there are, depending on the metal, colors of light that don't cause the photons to kick off. No matter how brightly I shine. The electrons? Yeah, the electrons. They don't cause the electrons to kick from the metal and travel on. No matter how bright I make the light. And normally in classical electrodynamics, right, we were able to discover and realize that the energy of light is proportional to the intensity, the brightness that I shine the light at. So if I'm making it brighter, I should be increasing the energy that I'm giving to the electrons. So they should eventually, as I make it brighter and brighter, kick off. But no matter the level of brightness that we were able to put on there for certain wavelengths of light, was able to kick off electrons. And this is reconciled by saying, oh, no. The light that you get from here, the energy is able to deposit in discrete packages, and each of those little packages, depends on the frequency, the wavelength of the light, the color of the light itself. And as I increase the brightness, yes, I'm increasing the average energy because I'm increasing the number of photons, the little packets that I'm sending onto the plate. But if the plate can't absorb any of those packets, then of course the electrons aren't going to kick off because they can't take the energy they can't accept the energy to get kicked off and move across the electric tube to get the kinetic energy.
So you haven't met the minimum energy level required for the jump.
Right. And that is explained by having light interact as if it were a particle. And so we had a phenomena where we had a highly accepted wave-like phenomena, light, all of a sudden needing to also be a particle. And it didn't take, like I said, it didn't take long for a gentleman by the name of Broglie to go, we've got this phenomena called matter that we very much think should be particles. I wonder if maybe we can find wave-like properties of this. Well, how do I check for wave-like properties? Oh, simple. I do double slit experiments. I try and get it to diffract through to get these, I try and get the material to diffract through something and see if I get interference with itself. Right? Interference is what happens when a wave is present in your system. So the way that it was actually implemented was a method done in just 3 years later in 1927 by Davison and Germer.
Less than 100 years ago.
Yeah.
We were still not even sure about these things.
Well, they set up like this. So you have an electron beam. You're just able to excite electrons. And you hit it into a nickel target, and then you have a movable detector that will pick up whether the electrons are there or not, right? Whether the electron that I shoot out comes there. And so you repeat this a number of times, right? You repeat this a bunch of times, and depending on how this electron beam is set up, usually it'll be sending out a continuous spray. And as you move the detector, you can say, oh, okay, I've got, this much. You keep track of how many counts it detects as you move it through the angular deflection. And if electrons are right, and the basic model of the nickel target is that it is, since it's a metal, is going to be a regular lattice of nickel atoms, right? You've got this, and then maybe you've got, so you'll have a lattice that looks like this, and that continues on through the thickness. But you have electrons coming in, and so they should come in and hit and deflect off, right? That's what I see and think about when I'm looking at little electron bullets, little electron particles, right? And you can think of a particle as a bullet, right? So what I would expect is that I would expect that there is a region of highly densely focused atoms, right? Where densely focused electron detection. And then as I move out from there, it gets less and less and less likely to happen where I detect an electron. Very similar to the picture that I would have with a single slit, right? I would expect here, instead of, obviously this is for photons, but I would expect if I were to visualize this, I would say, oh, okay, brighter is going to be more likely to see the electron that's fired there, and lighter and darker is, okay, the probability is lower and lower and lower. And I would expect a pattern like this main one here, where it's bright, lots of electrons being detected, and then as I move out, I expect less and less and less. And maybe you could have diffraction, and just like how with the ray light, the ray theories of light, you could potentially have some diffraction and still kind of deal with it without having to say, oh, okay, it's waves. But when Davison and Germer actually set this up, the pattern that they found was in fact much more akin to a double slit pattern, where there was regions of where the expected region of brightness of high probability of seeing the electron was broken up and subdivided into regions of places where you do see the electron and then regions where you just don't. You never observe the electron at this angle, which indicates that the electron acts kind of like a wave. And the question is, a wave of what? Well, the conclusion that eventually was settled on is it must be a wave of probability, a wave of likelihood of where you'll find the particle.
That's a heck of a leap.
Right? I'm jumping through a bit of science here and a bit of, a long period of going, what the heck do we do with this?
So basically what you're saying is they observe that.
They observe effectively an interference pattern. There must be a wave of something.
Right.
And what's interesting is that whenever you're doing these detections, effectively what happens is that only like a single dot shows up on your detection, either detection paper for a charged particle or some sort of detector. So you'll get one count that pops up for there. Now, of course, since this electron gun, if you're sending out a sputtering, right, it's possible that, there's a lot of electrons all at once flying through the air.
Right.
So maybe what's happening
is they're interfering with each other.
Is that, as they're bouncing through, it just happens that they develop an interference pattern because of the way that just, maybe some sort of statistical mechanics feature causes this wave-like thing, right? And maybe, so a probability wave because of the dynamics of multiple electrons just kind of bouncing into each other. Here's the trouble. Because you can tune your electron beam, and you can make sure that you are firing 1 unit of charge at a time, right? Millikan had figured out what the unit of charge was at the end. You can make sure that, I shoot 1 electron at a time, and that there's a pause for a long period before the next one is shot. And what's interesting is that if you let the experiment run long enough, you see the same pattern fill in, regardless of the fact that you're only shooting 1 electron in at a time, which means each electron doesn't have another electron to potentially, stat mech your way out of this problem. The electron itself has some sort of wave-like property. Because if it didn't, you wouldn't see a diffraction pattern. The fact that a diffraction pattern exists means it has to have wave-like dynamics. And what Broglie, when he actually initially proposed this, is that why would I expect, if I see wave-like, particle-like duality, we know that we now know that light has to have some features of a particle, even though it acts like a wave most of the times that we interact with it. Why then wouldn't I expect wave-like properties from things that I know must be particles most of the time? And so what he proposed is a very simple formula, is that, all matter actually has a wavelength to it, right? A wavelength, called the de Broglie wavelength, that's simply the Planck's constant divided by the momentum that it has. H, which always shows up in quantum phenomena, divided by the mass times the velocity that it's going at. So if I have an electron moving through this material, it will behave as if it has a wave according to this measurement. Now, here's the interesting piece of this, is that since an electron is a charged particle, you can actually set it up so that the nickel will indicate where the electron hits first, right? The electrons that you're shooting out. Or effectively, you can set up what is effectively a double slit experiment and have a detector that says, I sensed an electron moving past a negatively charged particle moving past slit 1 or slit 2. And the moment that I set that up, your diffraction pattern disappears. It materializes into dust, and it's all of a sudden back to what I would expect if I shot a bunch of little bullets at a double slit, where I've got mostly two bright spots, mostly centered behind the two slits. And what's interesting is if you actually have the technical prowess to make a photon detector that doesn't destroy the photon, you can do the same thing with light as well. The diffraction pattern of the double slit experiment disappears if you take out information about where the photon is. So depending on how you measure photons and electrons, you can force it to be wave-like or not. You can force it to be either wave or particle. And so this is the
choosing to detect which slit it goes through or not detect.
Right. So depending on how you measure your system, will determine whether your system looks like it's a wave-like system, or whether it looks like a particle-like system. And this is the first instance of the weirdness that is quantum mechanics, the breaking down of things that we take for granted in classical mechanics that just disappear and have to be reckoned and mixed together, get twisted when you go to the quantum world. And it's what we call wave-particle duality. Your experiments what type of phenomenon you'll see depends on the way that you design your experiment. Right? If I measure when I'm measuring something, the way for quantum mechanically, the way that I'm able to do that is because, I can't, it's not big enough to have multiple detectors set up at the same point in space. Everything that I'm measuring a single measurement at that point, right? So like the detector that we had here, right, this movable detector, at this, that broke it. Right? This detect at this point in space, the only thing that it's able to detect is, are you here or not? And then from the spread of that, what it's able to effectively determine is what was the velocity that the electrons coming out of this electron beam, what must they have been? But if I put my detector here to tell me where do the electrons hit, I'm measuring position. So if I'm measuring position, I'll get something particle-like. If I'm measuring momentum, I end up getting something wave-like. So the thing that I choose to measure affects how the system behaves. Ultimately, it interestingly enough, it forces the system to determine in one way to determine you want this information. Well, I'll give you this information, but you're giving up information in the other region. It's
because the point being is if you had put the detector at both ends to try and get the velocity and the position, you would always get particle-like results at that point.
Right. And you'll lose your ability to tell the momentum from the spread of whatever, wave-like diffraction you would have, right? Because ultimately, if I have, right, if we go back to this picture here, based on where the peaks, right? Remember this picture was the green lines were troughs. They could be troughs or peaks, doesn't matter. Mm-hmm. But the separation between between two lines would be specifically associated with the wavelength of that wave. That's what we call it. And according to Broglie, that wavelength is directly determined by a momentum. So when I see wave-like properties, I'm measuring momentum of some sort. But when I'm trying to figure out position, I give up my ability to understand and to get too much information about what the momentum is. That's what happens when the diffraction pattern disappears. I've lost my ability to measure the momentum this guy is coming at from here, right? And it's what scientists call complementary behavior. You measure one, you give up information about the other. So the question then is, how do we find the line? How do I go from a qualitative statement of, oh, okay, if I measure one thing, I lose information about the other? This is this is defined and expressed very nicely in the next quantum weird piece, right? What we call, thanks to the guy who really proposed it, the Heisenberg uncertainty principle. So you can quantify the amount of information you give up for one thing when you measure another. Okay? So to really tease out the Heisenberg uncertainty principle, I think it would be a good idea to look at an example. So what we're going to look at is the quantum harmonic oscillator.
Now, so just so we're clear, the Heisenberg uncertainty principle is going to tell us if we measure one thing or a certain percentage of one thing, how much of that we can know, like how much precision with which we can know that thing and how much it will constrain our precision in the other thing that we measured.
Yes.
So there is actually a smoothness here. It's not one or the other.
Right. Because of the one or the otherness has basically been about with the way that we're, the way that you would measure, for example, the position, which slot did the electron go through in a double slit experiment or photon, whatever particle you're looking at, wavicle. If I'm measuring that, then I'm very much limiting down where the particle had to have been. So I'm making a very precise measurement of the position. When I am asking, when I'm looking at the diffraction pattern, I'm making a very precise measurement of what the momentum of the particle should be. As long as I don't, have those detectors figuring out where the electron was, where the particle was.
And you're extracting the momentum based on the wavelength, which is shows in the distance between the little hotspots.
Exactly.
Okay.
Yep. The distance, because the distance between your bright pictures will be exactly corresponding to the wavelength separation, right? You can just do a little bit of math, and it's pretty easy to tell what the wavelength is based on the separation of the two bright spots in your on your detector. Yeah. So, quantum harmonic oscillator. And we're just going to go through the process of solving a quantum system. So, the first part is that we've in a previous talk, we went through the basic postulates of quantum mechanics. One of the very first ones is, well, if I don't have a system where its potential evolves with time, then everything follows the dynamics of the time-independent Schrödinger equation, which is, okay, the Hamiltonian acting on the wave function of my system is just equal to an energy times that same wave function. Effectively, what you're looking for here is the eigenvalue of the wave function. I'm looking for
the E.
Right. I'm looking for potentially the values of E and the functions that solve this equation for those possible values of E. What this basically boils down to is a differential equation, because H, right? H is a Hamiltonian, and so that's basically saying, oh, okay, a Hamiltonian, the left-hand side of this equation, ends up being H bar squared divided by 2 times the mass of whatever particle you're looking at. You have your wave function plus what we will call a potential that depends only on the position. And if it depends only on the position, then you have a time-independent wave equation multiplied by the wave function. And then that should equal some constant times your wave function. So I want to go through how to solve this. Now, so your system then is determined by what your potential is, what this V term is.
Now, what is a harmonic oscillator, and why do we put the word quantum in front of it?
So a harmonic oscillator is something like the pendulum in a grandfather clock, right? That's the first order approximation for that thing. If you don't move it too far, it acts precisely like a harmonic oscillator. And it's basically something, or a spring, right? It's something that follows Hooke's law, that there's a center point of equilibrium, and as I move away from that point, there's a force trying to restore it back to that point, right? In classical terms, right, the force acting on your object as a function of distance is equal to negative some constant times that distance. So as you push, as x gets bigger, the force is pushing against the direction you are making it bigger in, right? If I make it positive, then it's pushing me in the negative direction. If I make it negative, it pushes me in the positive direction.
And the more I pivot this thing up, the more gravity's going to try and pull it straight down. So
that's why a pendulum is an example of that, because with a grandfather clock, as I pull it from that equilibrium point, gravity comes in and says, no, go back. Minimum potential, minimum distance, get as far down as possible, right? Mm-hmm. Now, because of the way that energy conservation works, if I pull it up and then let it go, right, it'll get to that minimum point, but then all of a sudden it's got a bunch of kinetic energy, and so it moves through. And so you have an oscillatory behavior back between the two highest points that pendulum can have. And everything that we do mathematically in quantum mechanics basically has its footing in being adapted from classical mechanics. And what we discovered in classical mechanics is that you can capture the behavior of the system. Instead of looking at the force, you look at the potential. You look at the thing whose derivative gives you the force. And if I can understand that object, I can predict all of the dynamics from that potential, right? So in quantum mechanics, we do the same thing. If I know the potential that I'm putting my particle in, my quantum mechanical particle in, then I can predict all of the behaviors that system will go through. So here, for a quantum harmonic oscillator, it's pretty simple. Your potential, your thing that depends on distance, is simply the mass times some frequency squared, I'll call it, times your distance squared away, divided by 2. This is very, very, actually, since I gave you r, I should also be consistent with my variable, that. Right? So the potential looks like a parabola, where at the bottom is the minimum amount of that potential. That's where you set your equilibrium point. And as I move up, the energy needed to move to the left or the right follows a parabola, follows a parabolic equation. So solving this is in a question of, how do I find the eigenvalues of energy? And for a harmonic oscillator, right, it turns out that the easiest way to think about this, or to quantify the states, is to just say, my wave functions are going to be things that track the steps of energy that I have in the system. Because the beauty of quantum mechanics, when you solve the system, what you find out is that, there are levels that I can have. The first one, right, the ground state level, n equals 0. Then I can have one step up the ladder, n equals 1, n equals 2. And the energy that the system has, if it's in that state, is simply h bar omega n, I believe is what it works out to. Real quick. Yeah. So the easiest way to, and so these states, these n that tells you, the collection of all possible, and so from 0 to infinity, are what we call the pure states of the system. They are the eigenvectors of this equation. So when I plug in a state and hit it with this operator, this Hamiltonian operator, it gives me back the same state multiplied by some constant. In this case, that's your E. And that's what you do. That's what you're looking for when you're trying to solve these quantum mechanical systems. Anytime I'm trying to understand the dynamics of a small scale, quantum world system, I'm basically having to find what is the potential of this system, and then what is the eigenstates, the things that solve this differential equation, what are those that pop out? Both of those steps are very hard. It's very hard to find a good approximation for your potential as the system gets more and more complicated. Mm-hmm. And by more and more complicated, that could be just more and more specific. Knowing that I have a little box of copper atoms specifically that I've got an electron moving through. That's what you would be doing effectively whenever you're doing condensed matter. And then trying to account for the fact that that little bit of copper is finite. Right, if I have it really small, and so finite that the electron could sense the edges, right? These edge effects get complicated and difficult, which is why it's useful, at least as far as a conceptual level, to have very simple basic models, right? Harmonic oscillator. And the harmonic oscillator is really useful because it's the first simple system that can capture behavior in both directions. And so even though if you know how something is right at a single point, you might not be able to, heat it up or cool it down too much beyond that and still be able to predict the behavior, but you still have a pretty good shot if you know how it, behaves like a quantum oscillator in that point. As Feynman once put it, it's a question of, we see harmonic oscillators everywhere. Is that because nature actually, and he wonders, is it because nature actually is like that, or we're just not creative enough to find a better tool to better describe this?
Everything looks like nails to a hammer.
Yeah, we're just like, Taylor expansions. We always love our first order Taylor expansions.
Is our tally light still on this guy?
Yeah, okay. We're fine. It's still recording. All right, so let's say I've got a system and the zero state. The question is, how would I mathematically here change its thing? Well, I'll define a couple of operations that I can do to it, right? The operation of hitting the Hamiltonian is the process of telling me what's the energy that you have in your system, right? I would hit, right? So if I wanted to know what is the expected energy of some state, well, I would, hit it with some generic thing that is actually here.
Pull him up a little bit.
Yeah.
There we go.
So, I guess the easiest way would be to first define some probing state. I'll call it phi, actually. Like this. And this is equal to the sum from n goes to infinity of all the possible states. So if I wanted to know the energy, the way that I would look at this would be to take whatever value my system is in, let's say it's in the zero state, hit it with the Hamiltonian operator, and then say, oh, okay, let's probe all possible states. So this will end up being, because the way when we discussed this before in quantum mechanics, but the basic gist is, if I have one probing state hitting the wave function, it will equal a delta function, where if n prime and n are the same number, then you'll get 1, and if they're different numbers, you'll get 0. So that means that this equation here ends up being equal to 0. Right? And then you'll have the energy of the zero state. And then since this is a constant, we're able to pull it out of being sandwiched in between the two operators. And there we go. Like that. right? And so this will be 1. So I get, oh, okay, the energy of the 0 state, right? That's how a sample calculation would look like, right? Now, the probing the energy isn't the only thing that I can do to a quantum operator. I could and here I'll define it, the operator of taking a particle that's in the 0 state and saying, oh, I've given you some energy, now you're up 1 level. And that's what are called, these are the ladder operators. They are the things that let you go up and down this, what looks like a ladder, because you've got rungs, you know, that you can, one above the other. You can climb either up or down. And the way that works is that you have a dagger, which if it hits the quantum harmonic oscillator in the state N, then it's going to give you this output. It will give you the square root of the next ladder rung times the next ladder rung state, right? So it steps you up and then gives you the square root of that state as the constant that appears in front of it, right? You also have A, and if that hits a generic state in, that'll give you the square root of the state you're currently in, but the state below what you're at. Okay. Now, these aren't things that I can actually measure, but the things that I could measure, I can describe in the terms of these ladder operators. So I could ask, for example, what is, my position, right? Or what is my momentum? And again, according to the language that I described up here for energy.
What does that doohickey next to momentum?
That's supposed to be a question mark.
Oh. With
a little dot, because again, terrible at drawing.
Okay.
I wonder.
I question your question marks.
Yeah. Oh no, they're awful. Particularly when I have it set up like this. It turns out that trying to do these two things at once makes life difficult. Hooray.
So would it help if I get you a larger tablet that you can write on like a piece of paper that's not reflective?
What would really help is if I could like hunch over this thing, but I've got my computer in the way.
Oh,
so, yeah.
Okay.
Well, we'll have to fiddle with solutions later. Yeah.
Okay.
Anyways, so if I wanted to know what's my position or what's my momentum, right, the way that I would kind of go about this would be, average of X would be, a probing thing times whatever I'll define as the X operator on whatever wave function my system is in. Okay. The same thing, right? The way that it would look would be, there's going to be some momentum operator that will act on the wave function that my system is in, and then this probing state will tell me, oh, okay, which of the pure states pop out, right? Because any physical state that I could want to capture won't necessarily just be the pure states, the eigenstates of the Hamiltonian operator. Instead, what I'll have is that the wave function, right, like here, will be some linear combination of the pure states, right? So you'll have, say, a total of half of your function is in state 0, but there's a quarter bit of state 1 and a quarter state of state 4. And that could be the state that your harmonic oscillator is currently in. And because of the way that linear algebra works, I'll be able to spread it out and hit just the pieces that I know. If I'm predicting it's got a combination of 0, 1, and 4, I'll be able to look at the interaction of my probing state with 0, 1, and 4. Right.
Right.
So what are the operators for the momentum and position? Well, pretty straightforward. Since I have it in terms of ladder operators, and ladder operators naturally tell you how to move up and down in energy, that it's easiest to define everything else in terms of them, right? Because they give me the most straightforward mechanics. So the X operator is simply the square root of h bar divided by 2m omega, right? And remember, these things are defined by the mass of whatever particle is in a quantum harmonic oscillator potential, right? So it could be an electron in this kind of potential. It could be a proton in this kind of potential, right? And that's determines the mass. And then omega is a parameter basically telling you how wide or tight that parabola is, okay? So that's a little bit of information about the potential itself. And then it's simply A plus a dagger. Okay, so, a little raising, a little lowering, add that together, and then multiply by a particular constant, and aha, I've got the thing that'll tell me what the average position of my quantum state is, right? For position, similar, it's the square root of m omega h bar divided by 2 times a dagger minus a. And here's a little trick, a little weirdness. We put an I in front of it. Because when we're dealing with quantum mechanics, our wave functions are complex. They are allowed to take complex values. So I is going to show up. Now, this is why you can't actually call your ladder operators observables, because their eigenvalues, the things that, if I were to solve a similar equation to this with ladder operators, where, what are the vectors that give you back the same thing but times a constant? They would
come back with nonsense, basically.
Well, they would come back with complex numbers.
Right.
And then you don't know how to assign, it's hard to assign physical meaning to that complex number.
Right.
There are ways to do it, depending on the theory. For example, you can actually get complex numbers popping up in E and M because the exponent of a complex number, you'll get a magnitude times e to a complex number, and that magnitude, the magnitude tells you gives you information about the source that you're pumping into it, and then the exponent actually tells you how much that light, for example, or that electromagnetic radiation penetrates into the bulk surface of some metal or something. So there are ways to do it, but if you just generally have complex numbers running around for position and momentum, you're like, I don't know how to interpret that at all.
Right.
So one of the things about whenever you're trying to talk about observables in quantum mechanics is you say, the things that I can actually measure, they definitely have to have not positive. They have to have real valued eigenvalues, because the eigenvalues, as we discussed before on other things, are the possible results that you'll get for a particular measurement. So we have our X and our position and momentum operators. So we are currently in the way to figure out what is the Heisenberg uncertainty principle, right? Because these values here, right? Notice I've got these brackets. These are averages. So effectively what it will tell you is that it will tell you where the center of a distribution is. But there's still some possibility of other values, right? It's basically like I was saying, right? You're going to pick out, you can get to the end, the eigenvalues of this operator. So there's some chance, you'll get, say, a position of 1. There's some chance you'll get a position of -1, 2, etc. But the average is the value you could get times the likelihood that you'll get it, all added together, right, for every possible value you could get. So the question is, how much does the knowledge of the average bind, well, not even bind that because the average doesn't actually bind it. How much, having calculated the average, can you be assured that you'll actually find it in that region? Right. This is a feature, a standard feature of any time you do statistics, is wondering, okay, if I'm sampling from a random source, if I'm asking people their opinion on something, and then I know the average response, well, okay, just because I know the average response, I can't make a really great prediction about what any one individual will say.
The average home price does not tell you what a house looks like in LA.
Right.
Yeah.
And one thing that I can do to my data to try to figure out how tightly bound my data is to that average, basically how good is the average for predicting exactly what I'll see, is I can ask, well, what's the spread, or what's the variance of my data? And so the variance is a particular mathematical construct. Let's say I want to know what's the variance of my position. The way that I would calculate that is to take the square root of what is the average of the square of whatever I'm measuring. So what's the average of the square position, in this case, minus the square of the average, right?
Mm-hmm.
This is something that shows up, has been known for a while in classical probability theory and statistics. It's a very useful measure, right? Basically, if I have something that is a Gaussian distribution, right? The average tells me, oh, okay, where's the peak of this? And this peak, right? It could, the distribution could look like that. It could look, this is very bad Gaussian. It could look like that, right? And
right.
Knowing the difference between the two is very important. So the thing that will give me most, that's a little bit better, most accurately, help me distinguish what are these two, is knowing what is the width of these at a certain height, half max width or something. Right. And the thing that determines that is this sigma. Basically, this distance is from here to here. Let me get rid of that. From the center average over to here, that is the measure of my variance, right? And so knowing if it's small or if it's large, right, has a big factor. So for my quantum oscillator, I can, right, take this thing and square it. And so I'll get an object that looks, kind of like a constant. I can get x squared operator looks like one constant times AA plus another constant times a dagger plus a third constant. That's a dagger, right? And using the rules that I've defined up here, I can figure out, what a generic what would result in a generic quantum state, right? So if I wanted to know, okay, if I had any generic pure state in, right, I would ask, okay, what is in x squared in? And this would be, the average of x squared. You can do the algebra on your own. I won't force us to walk through it.
Mm-hmm.
But if I calculate what is sigma x squared without, taking the square root, what I find is that it is equal to h bar over m omega times n plus 1 over 2. I can also do the same for momentum, right? I've defined momentum in terms of ladder operators. I can square it. I know how the ladder operators will attack on general states. So I want to know, right, what is sigma p squared, which will be just what's the average of the momentum operator squared minus the average momentum, right? And this works out to be h bar m omega n plus 1 over 2. And here I'm going to consider an object. I'm going to look at I'm going to look at what is the multiplication of sigma x, sigma p, right? What's the multiplication of the variance times position and my variance in momentum? And that will work out to be, once I do all the algebra, h bar n plus 1 over, or plus 1 over 2, right? H bar n plus 1/2, which, so the minimum, right? Now this was the generic, one of the generic pure states, right? And n can go from 0 to infinity, but the smallest that I can get this, the smallest that I can get my variance between position and momentum down to is clearly by making n as small as possible. But for a quantum harmonic oscillator, that is simply 0. So the minimum joint variance I can have is h bar over 2. And this is the quantum uncertainty principle, the Heisenberg uncertainty principle. It's that no matter, as I get, as I get a tighter and tighter focus on one of these two things that I can measure, my position or my momentum. Let's say I'm bringing down the information I have on my position. So I'm making it a more and more precise measurement on where the particle has to be. Then I'm giving up more and more information on what momentum my particle could be at, right? That's pretty straightforward. A little bit of algebra tells me, oh, okay, sigma x must be h bar over 2 times 1 over p, right? So if I make sigma x 0, the only thing that I can do is to make sigma p this equation tells me the only value that sigma p could be would be infinity, right? Because that's the only thing that I can take the inverse of and get 0. Which means if I know exactly where a particle is to perfect accuracy, I know absolutely nothing about what momentum it could have. The same is true in reverse, right? If I know exactly what momentum it has, I can tell you nothing about the position. So this is the Heisenberg uncertainty principle for complementary measurements. When I have two measurements that would potentially conflict with each other, then quantum mechanics tells me the most that I can know about, the most that I can bring down my variance when I multiply the two is h bar over 2. And that's always, well, it's not always the thing. Now, I made the comparison earlier that, an important point, let me rephrase that. An important point is that not all measurements do conflict with each other. Sometimes you can make two measurements that at the same time on a quantum mechanical system, and that's not impossible to do. When we were talking about the Stern-Gerlach machine, for example, right? I've got a particle and I'm measuring how it splits in the XY direction. You were also asking about, well, why couldn't I also measure in the Y direction? You can. And the thing that in the theory tells you whether you can or not make the same measurement is actually a thing. It will tell you, you can figure out whether you can make two measurements at the same time on a quantum particle. And the thing that will tell you that is this thing, mathematical operation called a commuter. So let's say I have some property A and B, right? This could be X and P. This could be measuring X and Y. This could be measuring, momentum in the X direction, momentum in the Z direction, right? Then I can tell you if the anti-commuter of AB, which is effectively doing this, take the operation AB and subtract from it the operation BA. If the value that this is always going to give you on any generic wave function, if this is equal to 0, then these are compatible measurements.
Which means they can be taken simultaneously.
Yeah.
And I just want to point out, every single time the Heisenberg uncertainty principle is derived, I love seeing it every time.
Yeah, it's so
it never
beautiful.
gets old.
So what's interesting is actually, so you can have commutators on acting on generic functions. And so what's really cool is there's a generic Heisenberg uncertainty principle. You can tell, or based on the value of this commutator, you'll know what your Heisenberg uncertainty principle is. It's that my variance in operation A and my variance in operation B is equal to, or actually, no, not equal to, is always greater than or equal to 1/2 the positive absolute value of the average of the commutator of A and B. Right, an important point, because if I swap, right, if I,
Now, you quickly went through that top piece where you have x comma momentum, x comma y. So the one on the left is a position and momentum, and the one on the right is two positions.
Right.
Okay.
So I can measure two positions, right, at the same time. Or I can measure two different dimensionalities of position at the same time. I can also actually measure position in one direction and momentum in a perpendicular direction. And that's fine. That actually has a commutator of 0. It's when you try and measure position and momentum in the same direction that you have a commutator that's non-zero, and therefore an uncertainty principle between those two things. Yeah.
It's cool. I love this stuff.
Yeah. It's generic. And so now it's important to realize that it's not always just momentum and position that can be your uncertainty principles. You actually have an uncertainty principle between how much energy an interaction takes and how long that interaction takes. So if I want to know, if...
This reminds me of impulse.
Mm-hmm. So, for example, beta decay, right? I've got a thing sitting there, and it kicks off a proton and a neutron. If I measure the kinetic velocity of the proton and the neutrino that it kicks out precisely, then you know what I'm missing? I don't know how long that interaction took. I don't know how long it took the whatever was doing that beta decay, how long it took it to actually do that beta decay. All I can collect is the energy from that interaction. And in fact, that's going to lead to some other quantum weirdness. Now, an important note, uncertainty actually is not just a quantum thing. It appears anytime you have a wave-like system. You will have this uncertainty in like where your packets can be and how much momentum is actually in that wave. And more importantly, it's not a reflection of our measurement techniques. It's a fundamental limit in how sure you can be of a measurement about complementary information. That is, for example, if I come up with an apparatus that would tell me something a little bit about position and a little bit about momentum at the same time, this wave-like, in this case, quantum object, it tells me how much I can trust that measurement to be reflective of that system at any one particular time. Basically, if I took a measurement of the system and I knew the average, how likely am I to see that average again? Or if I use that measurement and see the quantum object in some state, or let's say some position momentum, how likely, if I turn my back and then look again, how likely am I to see it in that same position momentum? And how sure I can be of how likely I'll see it in that same position momentum, right? That's the fun, weird bit when you start to multiply together measurements, right? All right, so back to big picture. these two ideas, this wave-particle duality of what I'm measuring determines the behavior of what I'll see, determines the, what type of behavior my quantum system will exhibit, and the fact that there is some fundamental limit of how much I can pin down two pieces of complementary measurement are two of the basic building blocks of some very strange and weird quantum phenomena that really breaks with the expected reality, the expectations I would have about reality from what I know about the classical world, the macroscopic world. So next time, we're going to go through those other phenomena and show with a few, there will be a couple of pieces that we'll have to build up, but we'll build up those pieces and we'll show how, the quantum world is just so different in so many ways from our average everyday experience, and why it is so strange, and the background of knowing, it comes from the fact that, I can't pin down how that'll work out. So I'll see you next time.
So before you cut out, how are we going to tie this into quantum jumps? When are we going to get to cover quantum jumps?
So quantum jumps are a strange phenomenon of quantum mechanics. So that's next part.
Ah,
yeah.
Very nice.
Nice.
Benji, thank you very much as always.
Yeah, anytime.
It's a pleasure having you.
I will see you next time I'm around.